Hi guys, welcome to Real Convenience Telecom Academy, a channel that affords you the opportunity to study anywhere, at any time, and at your own pace from any device. That is how we define real convenience at Telecom Academy. As usual, this is electrical engineering technology, and I hope you are enjoying. If you are new, if you are accessing Telecom Academy for the first time, guys, don't forget to like, comment, or share, and above all, to subscribe. It is you who make this channel great. Welcome to DC Maximum Power Transfer Theorem presentation on Telecom Academy. And as usual, my name is Motion Marufu. Don't hesitate to get in touch with me on motionmarufuskis@gmail or on my WhatsApp +263 717 535 Guys, this is our last DC network theorem in electrical engineering technology. And I hope you have been enjoying whatever I've been giving you insofar as electronics, electronic engineering, telecommunication, you name it. And if you have been doing so and you haven't subscribed, hit the subscribe button and you'll never miss out on any updates on this favorite channel of yours. That affords you opportunity to study from anywhere, at any pace, and at any time, and from any device you have. Let us enjoy maximum power transfer. Objectives. Guys, this is what you should be able to do by the end of the course. Number one, you must be able to state maximum power transfer, a theorem that is in words. Then objective number two, you must be able to determine the value of load resistance for us to have maximum power transfer, that is from a given circuit. And last but not least, you must be able to apply the maximum power transfer. Just 3 objectives and we are done. A look at maximum power transfer theorem introduction, and we are proceeding. When designing a circuit, it is often important to be able to answer the following critical question. And the question is, what load should be maximum power transfer theorem can also be stated as, for a given source voltage, maximum power is transferred from a source to a load when the load resistance RL is equal to the internal source resistance. You remember source resistance RS when we did voltage sources and current sources, and we are saying the load resistance must be equal to the source resistance, right? How do you calculate RIL, or the current through the load? We said RL must be equal to R-Thevenin, which means to find current, we divide voltage by resistance, and these two resistors must be equal. Hence, we are saying total resistance is equal to RL plus R-Thevenin, but we know that RL is equal to R-Thevenin, so we can replace this RL by R-Thevenin. So it's the same as saying E-Thevenin divided by R-Thevenin plus R-Thevenin, and mathematically we know that R-Thevenin plus R-Thevenin is equal to 2 R-Thevenin. So this is how you find IL, or maximum power transfer to the load. This enables to find the current that flows through the load, right? But we know that the power dissipated by the load is equal to IL squared RL. We know power is equal to I squared R, but in this case I is equal to IL. Hence we are squaring that current and multiply it by the load resistance RL. We are now going to substitute IL. We have calculated IL, so we are now squaring this. So we are saying E-Thevenin squared divided by 2 R-Thevenin. E-Thevenin divided by 2 R-Thevenin. All this is squared and we multiply it by R-Thevenin. This R-Thevenin is equal to RL. Don't forget. And if we simplify this, we are saying power delivered to a load is equal to E-Thevenin squared divided by 4 R-Thevenin. Guys, you know your engineering mathematics 1. This is how you calculate power dissipated by the load for maximum power transfer theorem. We are now going to look at one special application of maximum power transfer theorem, and this is in audio applications like stereo, radio, or even public address systems. And in these systems, we've got a speaker, 4 ohm, 8 ohm, 16 ohms, and that will be our load. And that load, for the sake of our discussion, we are assuming it has got a resistance. So the resistance can be 4 ohms, it can be 8 ohms. ohms, it can be 16 ohms. The speaker, guys, we know from our hi-fi systems add to home. The speakers are connected to a power amplifier. They are connected to a power amplifier, and these power amplifiers are made so that they deliver maximum power to the speakers. So the resistance of the speaker must be equal to R-Thevenin, or must be equal to the internal source resistance of the amplifier. So for us to have what we call impedance match, we are saying the resistance of the speaker must be equal to the internal resistance of the amplifier. If they are not equal, then we won't have maximum power transfer. That is what we call impedance, or in this case resistance mismatch. You can find analogies of matching. For example, ladies do like to match the dress, the headgear, and even for their sandals. They always want to match. If they are putting on red, everything must be red. If they are putting blue, even the handbag must be blue as well. We call that matching. So let's look at the 5 steps that are followed when you are solving maximum power transfer theory problems. And step number 1, we are going to remove the variable load resistor RL. You remember this is what we did in Thevenin theorem. Then step number 2, we are going to find V-Thevenin across the points A and B. So after removing RL, we must mark 2 points A and B. Then we find V-Thevenin. In other words, V-Thevenin is our open circuit voltage. Then after finding V-Thevenin, we are also going to find R-Thevenin from the 2 points A and B. Then we are going to find RL by equating RL to R-Thevenin. You are done. In other words, your R-Thevenin is your RL. Then we are going to calculate maximum power that can be delivered to a load from E squared Thevenin divided by 4 R-Thevenin, or divided by 4 RL. And you are done. We now want to apply maximum power transfer theorem in finding RL, and we are also going to calculate maximum power. And the question goes, find the value of RL, and this is our RL for maximum power transfer in the circuit below. Then part 2 reads, find the maximum power. Right, let's go to the solution. How do you find RL? RL, first remove RL, and after removing RL, we are going to find R-Thevenin. How do you find R-Thevenin? Replace the current source with an open circuit and the voltage source with a short circuit. So the equivalent circuit, find R-Thevenin is as this, and we are finding R-Thevenin looking from this direction. From this direction, these 2 resistors are in parallel, and the parallel combination is in series with these 2 resistors. So the parallel combination has got a total resistance of 4 ohms from product over sum 72 divided by 18. This gives us 4. So we've got 2 plus 3 plus 4. This is going to give us 9 ohms. So the first part we are done, and we are correct. Our R-Thevenin is equal to 9 ohms. We are now going to find V-Thevenin so that we can calculate maximum power delivered to RL, and we are going to make use of Kirchhoff's voltage law. 12 volts minus 6I1 minus 12I1 minus, this current is going in the opposite direction, 12I2. I2 is going to flow through this, and this is going to give us 0. We know our I2 is equal to 2 ohms. So if you simplify, this is going to be 24 ohms. And if we simplify further, we are going to find a negative I1, and that negative I1 will be minus 2 over 3. The negative sign shows that the current is in the opposite direction to the direction that we chose. And our I2 we are given. Our I2 is close to 2 milliamps because we are proceeding in the downward direction and not in the, it is in the opposite direction to I1. So these are the 2 currents, our I1 and our I2. And we now want to find V-Thevenin. V-Thevenin is equal to, we can make use of Kirchhoff's voltage law, and this is how you are going to proceed. 12 minus 6I1 minus 3I2, this is a 0, so there's no reason for including it, is equal to V-Thevenin. In other words, 12 minus the voltage drop across this minus the voltage drop across this is equal to V-Thevenin. So our V-Thevenin is equal to 22 volts after substituting for I1 and I2. I2. I1, we have got it. I2, we have got it. If we substitute, we are going to get a positive value of 22 volts. So we now have got R-Thevenin and V-Thevenin. In the next slide, we are now going to calculate maximum power delivered to RL using the equation that we derived. We are now going to calculate maximum power, and how to calculate maximum power. The formula that we derived is E-Thevenin squared divided by 4 times R-Thevenin, or times 4 times RL, where RL is equal to R-Thevenin. So we are going to replace E-Thevenin by 22 and R-Thevenin by 9. If you square this and divide by 36, you are going to get 18.44 watts. We know power is measured in watts. So guys, as simple as this is how you are supposed to articulate such a question. Let's proceed to the next work example. Must be able to solve such kind of maximum power transfer theory problems. Guys, if you are enjoying, don't hesitate to hit the subscribe button. And also for you to receive notification of any uploaded videos, don't forget to also hit the notification button. Another work problem for you on maximum power transfer theory, and the question goes: the open circuit voltage of a standard car battery is 4.6 volts, and we know that V-Thevenin is open circuit voltage. So this is our V-Thevenin. And the second part goes: the short circuit current is approximately 300 amps. What is the power available from the battery? We want to calculate power, and open circuit voltage is equal to V-Thevenin, and short circuit current is the same as I Norton. So we have got V-Thevenin, but we don't have R-Thevenin. So we now want to calculate R-Thevenin, which is the same as RL. And how do you do that? This is simply V-Thevenin divided by I Norton. And our I Norton we are given as 300 amps. So we are going to get 0.042 ohms. This is a very low value. So this means that this is very, very correct, even from source resistance. The source resistance of a voltage source is a very low value. So this is bound to be correct. So we are now going to calculate available power, which is maximum power, and it is calculated from V squared Thevenin divided by 4 R-Thevenin, and we are going to replace with the values. We are going to get 945 watts. So easy, guys, and I hope you are enjoying it. You are loving it. Let us go. We are almost done. I think I looked at impedance match. Impedance match is when RL is equal to R-Thevenin A, or RL is equal to source resistance. That is, when the load resistance is made equal to the output impedance of the circuit, we say we have got impedance matching. But when they are not equal, we have got what we call impedance mismatch. And maximum power is delivered to a load when there is impedance match. Right? What is the significance or the importance of maximum power transfer? We often deal with a small amount of power in electronics. For example, to obtain the maximum power out of a circuit is very important. We connect what we call rabbit ears antenna to the TV set so that you are able to receive power from radiating waves. What do we mean by radiating waves? These are TV waves in space, or from ZBC, or from any TV station that beams into space. For example, we receive DS from South Africa. The antenna does not collect much power because radiated power is very, very low, especially if you are receiving something from South Africa. It will be very, very low. So what do? We design the TV so that it is able to make maximum use of that small power intercepted by the antenna. Antenna is another name for aerial, those satellite dishes we install at our places. What do we mean by optimization? In practice, we always have some constraints. When best possible design is made under the constraints, we say we have optimized the device. That is, the design is optimum. So our TV's receiver input is optimized so that it is able to receive maximum, or as much, so that it is able to process as much as possible radiated TV radio waves. And how is it optimized? Its input impedance. We know our antennas, our DS dishes have got an Ethernet cable that we plug onto our decoders. So we make sure the input impedance is matched to the output impedance of the antenna. Each antenna has got an impedance. That coaxial cable from the dish or from any antenna to our TVs or to our decoders has got an impedance, and some have got an impedance of 50 ohms. So when the input impedance of the TV is matched to the input impedance of the cable from the dish or from the antenna, we say we are going to have maximum power transfer to the load or to our TV receiver. If they are not the same, if the input impedance is not the same as the output impedance of an antenna, then we have got a mismatch and we won't have maximum power transfer to our TVs from the antenna. Guys, this is the end of our presentation on maximum power transfer. Guys, make sure you are able to state it in words. Make sure you are able to calculate other Thevenin, V-Thevenin, and also to calculate maximum power and also to describe application. I said it is most used in audio systems so that we can have as much power as possible coming from our speakers. Even at home, I know guys, you like noise. For you to have a lot of noise from your subwoofer, they must be maximum power transfer. So guys, don't forget, if you haven't subscribed, to hit the subscribe button, and also for you to receive or to be notified of any video that we would have uploaded onto our YouTube channel Telecom Academy. Don't hesitate to click the notification button in the comfort of your homes. Whatever an upload is made, you'll be able to receive it. Otherwise guys, until then guys, take care of yourselves.